record on this computer. There we go. All right, so yeah, so do Wednesday. I'll change the date to the 8th at 5 o'clock. Office hours will still be today at 3. If tomorrow works for you, and the 3:30 is what I set it up for today. I have no office hours scheduled tomorrow, but shoot me an email if you still got questions. And then, of course, Wednesday we'll have another office hours session at 3:30, and then it'll be due Wednesday at 4 o'clock. The worksheet for today is spherical harmonics because we're starting a new chapter, and that'll be due Friday at the end of the day as well. So those are the things we're talking about, and that's always how you can find it. Thank you, Pat, for pointing out that was probably not consistent with what I said, which I think I said was Wednesday, and yet I put Tuesday in as the due date. So we'll fix that. Do expect a homework to be coming out on chapter 3. Okay, so you'll turn in the last worksheet on Wednesday. Right on the heels of that will be a homework assignment on chapter 3. I'm seeing 3 problems right now. I could add a 4th, but I'm probably not going to. I think 3 will probably be it. And just as we transition over into chapter 4 here, I think you have to agree that in chapter 3, there really was no new material per se. Well, there was new notation, right? And I think you added a lot of depth to some of the things we'd already alluded to, like how do you find the probability of measuring a particular energy eigenvalue on a system? Well, I think you knew if it was a discrete eigenvalue case to find C and square it. I just kind of pushed that to you earlier in the semester. And one of the things chapter 3 does in and around this new notation is it tells you exactly why that has to be true. Okay, we did consider an eigenvalue problem other than energy. We started thinking about momentum and position eigenvalue problems, and that may be new, but we've been doing energy eigenvalue problems all through chapter 1 and 2, and we just weren't labeling them as such. And we were learning the rules of them. And of course, the rules for energy and momentum work the same, except we found momentum to be the continuous case, like the free particle that we worked back in chapter 2. Uncertainty principle, nothing new there, okay? What was new, of course, was the depth. You were considering the uncertainty principle for things besides momentum and position and energy and time. You were looking at other uncertainties. And so it's certainly a different chapter. It does set us up, of course, for things we're going to do in chapter 4 when we're looking at Schrodinger's equation in 3 dimensions, and specifically when we start looking at the hydrogen atom and some of the components of the hydrogen atom and the fact that they have angular momentum and that some of the other components we say spin, like the electrons. And so we're setting ourselves up with a way to talk about that in chapter 4 without having to do it the same way we did in chapter 2, where everything was a tedious long interval, because everything in quantum mechanics isn't related to an interval. In any event, that's kind of the introduction to chapter 4, I guess. And I'm going to start sharing my screen from PowerPoint with you instead of, hopefully that's the right one. Yep, share. And with any luck, you're seeing, come on. Micros, there we go. And I'll put this away so that it doesn't interfere with our video. And hey, Pat, since you're the one talking, can you see the PowerPoint right now? Still there, Pat?
Yeah.
Okay, somebody answered up. Thanks. All right. So everything we've done so far in quantum mechanics has been a one-dimensional problem, and you know that is a little bit unrealistic, isn't it? Because the world isn't one-dimensional, and so everything we've done has been over X. I don't even think I've gone to Y and Z necessarily. And hopefully you recognize this as the one-dimensional Schrodinger wave equation that has a time dependence to it. Okay. And, you know, one of the big points of chapter 3, as I just pointed out, is if you think about this Hamiltonian operator, which is all of this stuff right here, that should include the derivative, and that, it is just an eigenvalue equation, right? Almost. If only you did something with the left side. Okay, if only somehow this could be a constant times the wave function back, that would be an eigenvalue equation. And so that's what we did. We went to the time independent portion, and it was an eigenvalue equation. But this notion of operators was important. All right, well, so the shorthand way of writing this required you to understand that the Hamiltonian operator was momentum squared over 2m. Should never forget y, right? 1/2 mv squared. Turns out, yep, mv squared, that would just be p squared, but you got an extra m, so you better divide by 2m. And so this term right here, we recognize as kinetic energy, 1/2 mv squared. And of course, that's potential energy. I hate the fact that we use V because we mean V potential energy in joules. If that confuses you, think about me. I'm teaching PHY322, the introductory E&M class. And in that class, V is potential, electric potential, joules per coulomb. And so if I mess that up, correct me, but this V right here is really U, energy in joules. Why we go V, I don't know. But anyway, in 3 dimensions, okay, that we said the momentum operator in 1 dimension was just a derivative with respect to x multiplied out front by minus IH bar. In 3 dimensions, you got to recognize that there might be a y component of momentum, where I just take the derivative with respect to y, and a z component of momentum, where I just take the derivative with respect to z. And so while 1-dimensionally I can just write that, 3-dimensionally you recognize you got to have 3 components, okay? Each component of momentum might contribute to the scalar kinetic energy, okay? And so all you got to do is that, because this thing right here is a magnitude, it's a scalar, and we're good to go. Okay, and so what I'm going to do then is I'm going to square each of these guys, I guess, and plug them in. But just first, you could write the 3-dimensional momentum in this way right here, in which case the shorthand would be that. And all I'm doing is before I square it like I need to, I'm just writing that right there. And we refer to this sometimes because of this notation as the del operator. All right, well, I guess then if I want to take my 1-dimensional Schrodinger wave equation, I just have to put this in here, recognizing that it was a second derivative with respect to x squared here. It's going to be this del operator squared, right? And just so we're clear how we define a del operator squared, we take the dot product. This is the del operator. If you bring these si's outside, bring each and every one of them out there, what'll be left, actually, I mean this one first. Let's take the del operator out of each of those three and put it right out there. You'll get the del operator. I can do the same thing right here, bring those guys out, and what's left is this thing, which is del dot del. It's a del squared. We call it a Laplacian, right? And you do it, it's defined via the dot product. And so that's why I said, if you bring this del out here, you get the Laplacian operator right here, which means just take the second derivative with respect to x, with respect to y, and with respect to z. And so then I can write the time dependent, the one with the time. I can write the Schrodinger wave equation version in the most quick way, just by substituting in that Laplacian operator, that del squared operator right in there, and it takes the place of that guy right there with the 1/2m, or h bar squared over 2m, and the potential. That becomes a new Hamiltonian operator in 3 dimensions. Hopefully nothing that we haven't talked about in modern physics. I know for a fact, my internet connection is unstable right now. So that probably means my audio is breaking up a little bit. That's what experience is teaching me here. So I'll stall for just a second till it comes back. This should be nothing new. I know for a fact I taught this exact same lecture here with a little bit less detail in PHY211 modern physics, and I'm surely hoping that Campbell covered it for those of you that had him for modern physics. Anyway, so we're now in a 3-dimensional world. And so in 1 dimension, in this square box here, we talked about the probability of, say, finding a particle in between this range right here could be found from that. We recognize psi star psi is just this probability density function we call psi squared. And when we integrated it over all space, back in, I guess, chapter 1 and 2, we said that's our normalization condition. It just says that the particle has to have a probability of being someplace 100% of the time. You'll find it in between minus infinity and plus infinity. That's all we're saying right there. But now that we're in 3 dimensions, of course, dx here has to be replaced with something. Dx here has to be replaced with something. And the answer, and again, it's a little bit of notation issue. In a calculus class, you might have said something like dv, a volume element here, because it's a 3-dimensional integral. This is really a triple integral, right? Same thing here. And I'll just, if you've taken advanced electricity and magnetism class, and I don't even know who taught it. It would have been last spring, I guess. I think Campbell taught it, but I'm not 100% certain. In Griffith's electricity and magnetism book, the symbol for dv is a tau. And his argument for using tau is that, hey, in electricity and magnetism, as I already was talking about before, V is potential difference in joules per coulomb or volts. So that symbol's kind of used up. We don't want to use it. He chooses tau in his advanced electricity and magnetism book. Interestingly enough, in his quantum mechanics book, the one we're using, he uses this symbol, okay, which just means a volume element. That's why it's cubed, because it's meters cubed, right? And that's what this evokes. He bolds the R in his book. I probably decided that I'm not going to do that because bold typically means it's a vector. It's really not. But what is it? Well, okay, first of all, R here is a vector. And so rather than saying X and Y and Z in Cartesian coordinates, I'm just going to write R now for the variable and placing what used to just be X in one-dimensional problems, and time, of course. And you know, we've got three coordinate systems we look at. That's Cartesian, of course, X, Y, Z. Spherical coordinates, R and theta and phi. That's going to be the one we spend most of our time in chapter 4, if not all of our time. I don't think I'm going to do a Cartesian problem. And I'm debating whether or not to do a cylindrical coordinates problem, and I'm probably not going to, just because it doesn't add much. But and different people use different symbols here. I've seen rho used for the radius. I've seen R used. Griffiths in an advanced E&M book uses S. So those of you who may have looked at that have seen that notation. And then the angle phi, and then Z being in the cylindrical coordinates, the axis. Okay, and I do want to make a point about these coordinates. We're going to be spending most of our time in spherical coordinates. And in physics world, where we live, theta is the angle with respect to the z-axis. You'll sometimes hear me call it the polar angle. If you think about environmental science and how we do latitude and longitude, it's kind of 90 minus latitude, because latitude comes up from the equator, whereas theta comes down from the North Pole. Okay, so it's some people call it colatitude, but I'll often refer to theta as the polar angle. And then this angle right here in the XY plane, in physics world, we call that phi. Okay, I'll call it the azimuthal angle. If you're thinking about a globe and how we do coordinates on a globe, it's just like longitude, except longitude goes plus or minus 180, and this thing goes around 360, 2 pi radians. And the only reason I point that out specifically is if you've taken a math course, it's very likely that the mathematicians invert the meaning of those two angles. They call the polar angle down from the North Pole, they call that phi, and they call this angle in the XY plane here, they call it theta. And so very often when a mathematician looks at cylindrical coordinates, labels that angle right there as theta because of it. And you know, if R and theta are your polar coordinate angle dimensions in 2 dimensions, coordinates in 2 dimensions, then you know that makes sense. And nobody can agree on this, and I'm not going to even try. But I guess the bottom line is, in the notation that Griffith uses, it's this. And so I just want to be clear what we mean by this volume element, which is d cubed r, or if you've taken the E&M course, d tau, or maybe in a calculus class you called it dv. In Cartesian coordinates, dx, dy, dz. In spherical coordinates, r squared sine theta dr d theta d phi. And by the way, if you're using a mathematician notation, all it really does is change that from a sine to a cosine by virtue of the fact that you flip the angles. And I've had to put up with that, and so will you. Any event, dr d theta d phi. And then in cylindrical coordinates, the volume element would be S ds, or rho d rho, or r dr, whatever you want. Then the angle differential and the z coordinate differential. Any one of those will be volume elements in any of the 3 coordinate systems that we use. And again, we're going to focus mostly on spherical coordinates. All right, let's make sure I'm okay here. Yeah, I'm good. Still want to make sure that nothing went wrong with my recording. What's the general solution to Schrodinger's equation in 3 dimensions, the 3-dimensional Schrodinger's time-dependent wave equation? And the answer, you would hope, is this capital psi of r and t, and then some, we call it a stationary state, I guess, that comes from solving the independent wave equation. And then we always tack on what Griffiths refers to as this wiggle term. That's just an oscillating term because it's I omega t, right? And that's what's going on. It turns out, and I think we've seen it, if the potential energy is independent of time, this is a complete set of stationary states. And just there's a whole bunch of them, and could be infinitely big. It could be too big, but there's a whole bunch of states. And if I ever want to find these stationary ones, what I have to do is solve the time independent Schroeder wave equation in 3D, which we also called the energy eigenvalue equation, because it absolutely is what I was talking about at the start. It is that. Okay, so I operate with the Hamiltonian operator on this lowercase psi. I return an eigenvalue. It happens to be the energy times the wave function back, and that's what we were talking about significantly in chapter 3. Okay, so that right there causes me to solve this thing here, get the solution to that thing there, tack on the wiggle term, and that is the complete set of stationary states that we can have. Okay, and like any differential equation, once I have one solution, and then I can find a second solution, perhaps maybe n equals 2, and a third solution, n equals 3. The sum of all those is also a solution. That's kind of a general principle of differential equations. If I keep finding solutions, then all I have to do is add those solutions up in linear combinations, and that sum becomes a solution itself. Of course, the hard part is figuring out what the constant associated with each of those solutions is, and that is, of course, figuring out the Fourier coefficients, because that's what that is. But that thing had a significant statistical interpretation that we proved with new notation in chapter 3, but you had done in chapters 2, and even, I guess, back in chapter 1 a little. Now it's just chapter 2, was that thing had a meaning. Once you square it, that was the probability of getting a particular energy, right? And so that was an important guy. General solutions, we're doing it now in 3 dimensions. That's x, y, and z, or r, theta, and phi. Same thing right there, okay? But the energy, still the same right there for a particular state. All right, great. I just want to review coordinate systems. If you used Griffiths' E&M book, you have it. This is the front cover. I just kind of chopped it up a little bit because he does a nice job in one place putting the Laplacians, which you might need, Laplacians in any of the coordinate systems. And of course, the one we're going to be playing with today is that one in spherical coordinates. I just want to point out which mathematicians spent a lot of time doing work in these areas and who gets credit for them. See, Fourier gets credit for working in the easier system, Cartesian, because in Cartesian coordinates, the solutions to equations that have these kind of things, gradients or Laplacians or divergences and curls, are often sines and cosines. Okay, and Fourier did a lot of work with that. And so solving a Laplacian equation in Cartesian coordinates gets you sines and cosines, and Fourier was the mathematician responsible for a lot of that. Cylindrical coordinates and solving a differential equation that maybe had a Laplacian in it was the work of Bessel, another French mathematician, and he gets credit for a lot of that. I first came into contact with Bessel functions and learned most about them when I was learning to operate a nuclear reactor for the Navy, because all our reactors are cylindrical in geometry, and so things like neutron flux and heat fluxes all were cylindrical coordinate differential equations, and the solutions were often Bessel functions. And I knew a little bit about Bessel functions from my physics acoustics days, but not much. But when you have an application where you have a cylindrical symmetry, Bessel functions are key to learning about that geometry. But for us now, atoms are typically spherical in symmetry. Okay, and so spherical coordinates are going to be the important thing, and you'll see them in advanced E&M if you've already taken that course, or if you plan to take that course. The mathematicians that worked on that are Laplace and Legendre, and in fact, the solution to the differential equation, oddly enough, the differential equation in E&M is called Laplace's differential equation, and the solution to it are called Legendre polynomials, or perhaps Legendre functions. And so those are the two guys who get credit for solving a lot of mathematical work in spherical coordinates, and we'll see their names today here. Okay, so why is spherical coordinates the thing we're going to use when we're trying to describe an atom? Well, I'm sure you can see that that an atom has spherical symmetry. That's what you've probably been drawing atoms since you were in grade school. But the bigger issue for us as physicists is in Schrodinger's wave equation, that V term for potential energy does decrease with 1 over r, And then, of course, the direction of the field that's associated with it, not showing this guy, that's a scalar. The direction of the field is radial in many cases. And that's true for gravity. That's true for electrostatics. And of course, we think that an atom is kept together by an electrostatic force. And so the electrostatic potential is one that plays. And I guess I'd ask you, can you think of a potential that doesn't only vary as 1 over r here and have a field that is radial? Okay, so this is field is what I was trying to denote there. It's not associated with the potential. Potential is a scalar, but a field is radially outward. But that is the characteristic of a 1 over r, what we call a central potential, is it does vary like this and has a field that's radially outward. By the way, the answer I came up with that most of you probably saw was dipoles. If you think about a dipole, in addition to varying with distance, which isn't 1 over r, by the way, in potential, it's 1 over r squared, but it also varies with angle, doesn't it? Because if I had a dipole and you wanted to find a potential right here, it would be completely different than, say, the potential out here, because there's a sine of theta term usually in the dipole potential that you have to account for, okay? So that's not a 1 over r potential if you got a dipole, but atoms aren't dipoles, right? And that, you know, a particular atom is more like a monopole, and it is a 1 over r potential, central potential, and that's what we're going. Our spherical coordinates handle that really well. I should point out, and you may not be aware, there is a magnetic field potential as a symbol A. It's a vector. So the potential associated with a magnetic field is not a scalar like V for electrostatic case. It is actually a vector. And you take the curl of it to find a magnetic field, as opposed to taking the gradient of it to find an electric field. Stuff for another day if you're in the course. Anyway, I repeated the spherical coordinate stuff, and of course Schrodinger's wave equation deals with that. And that means we're going to be playing with this guy here today and plugging it into the Schrodinger. We'll go the time independent, the energy eigenvalue problem, to figure out what the wave functions are associated with spherical coordinate things like atoms. Okay, and so time independent Schrodinger wave equation, the energy eigenvalue problem, if you will, and right here, I'm going to take this thing from the previous slide. And by the way, I should tell you this: if you ever feel like you got to memorize this thing, my advice would be to spend your time on something else, because I've been doing this now since the late 70s, and I don't have it memorized. I have to look it up each time. But you should see the characteristics of it that make it look like a Laplacian, because the Laplacian in Cartesian coordinates is 3 second derivatives added together, right? And you go, okay, well, where are the second derivatives here? And well, there's a first derivative and you're taking the derivative of it. So that is a second derivative, but it's also a product rule, right? So this is really 2 terms if you wrote it out differently. And you will see some authors write that out as 2 separate terms, right? Because you could do a product rule on that. And then one of them would be a first derivative and the other will be a second derivative. Same thing right here. You got a second derivative, right? But it's also a product rule. So one of them will be a first derivative, one will be a second derivative. So there's really 2 terms being combined right here, 2 and 2. There's 5 terms in this Laplacian, I guess, aren't there? This is explicitly a second derivative, which is what you would want it to be. In any event, all I did was take that guy, jam it right into there, and rewrite. And I guess I need to do something. I need a technique to solve this thing. And the only way to do it is, that I know of, is separation of variables. And what we're going to do is we're going to assume that these guys, okay, these psi's, these energy eigenvalues now, are going to be replaced by a function who is only a function of r, and then another function, y, which is only a function of the 2 angles. Okay, and so we're going to jam that right in there, right in there, right in there, 5 places, right in there, right in there. Okay, we're going to rewrite. And that's all I did. And I dropped the fact, because hopefully it's obvious, the big R function is only a function of the variable r, and this y function is a function of the 2 angles. By the way, we're going to call y the spherical harmonics. That'll come back here in a second, and I'll just call r the radial function. And of course, I'll drop the fact of what they're depending on as I plug it in here. Okay, so that's all I did. That's this next line right here. I plugged in for the wave function psi, the product of r and y, the radial function, and the spherical harmonic, which is a function of the two angles in spherical coordinates. And then what you notice I did is I brought that guy outside the derivatives. And let's see, in this one, I brought that guy outside the derivative. And I guess this guy, I brought that outside the derivative, and that's why they're there, there, and there. And I guess the question is, okay, what's my justification for that? Well, if y, for example, here is only a function of the two angles, then taking a derivative with respect to r, you treat y as a constant, and it came outside. In this case, I'm taking a derivative with respect to theta. So r is only a function of r, it comes out. It's treated as a constant, same thing here. And so I did that step. Griffiths just blows right through this stuff and leaves you with an equation then that looks like this. Because once you got that done, you brought those things out front, the next thing I'm going to do is, well, I'm going to divide through by psi, which is the product of the spherical harmonic function and the radial function. So I divided through by yr right there. That wasn't there in the previous line. That wasn't there. That wasn't there. That wasn't there. I divided those through and I canceled what I could cancel. And I should be careful here. The only thing that cancels here is the y, the r persists. The only thing that cancels here is the r, the y persists. The only thing that cancels here is the r, the y persists. They both cancel here, and so I got b plus e. Okay, and so moving along here, I guess I'm making progress. I'm trying to separate each term to only be a function of, say, r by itself, or the angles. And that's my goal right here. And so the next thing I'm going to do, this means multiply by minus 2m r squared over h bar squared. And you can look out front, you can see, well, that makes perfect sense to multiply by 2m over h bar squared, because that'll cancel that with the negative sign. But why the r squared? Well, if you look, if I multiply every term by r squared, this term, which is mostly angles, I bet I'm breaking up right now. I get a pop-up says my internet connection is unstable. This guy here is a function of angles, but it's got an r squared term I'm trying to get rid of. This guy here is a function of angles, and it also has an r squared term. If we can get rid of it just by multiplying through by r squared on every term. Okay, so that's what we'll do. And that gets rid of that thing out front. Gets rid of the r squared there, gets rid of the r squared there, gets rid of the r squared there. And of course, the whole term has to be multiplied by both v and e. And if you notice, I brought e to the other side of the equation right here, so it comes over as minus e. And I did that before I multiplied everything through by minus 2m r squared over h bar squared. Okay, a little bit of manipulating now. I don't have these constants out front, so I can get rid of the square brackets. And I noticed that this term right here only varies with r, so I brought it in, I guess, right about there and associated it with this term, which also only varies with r. And then everything that was left, which I think was the second and the third terms here, I wrote right there. And sure enough, I think I've achieved the goal of separating variables. Everything that I put this kind of square bracket, this first bracket around, is only a function of r. And that was including this piece here with all of that piece is only a function of r. And then everything right here is only a function of the angles, theta and phi. Now, the technique, once you have separated terms like this in a differential equation, is you say, well, can you imagine a math function, okay, r, whose derivative, multiplied by r squared, taking a derivative again, slap some constants in front of it with multiplying by r, that thing changes exactly the same as this guy does. Now that's a function taking second derivative with respect to one angle, taking a first derivative with respect to an angle, multiplied by sine of theta, taking a derivative again. Can you imagine two math functions, r and y, where you can do all that to, and there's any way to add up those four terms and have them add up to be zero? And mathematician, that's the mathematician challenge, right? Can you come up with two functions like that? And the answer is, of course you can't, okay? You could probably try from now till the time you die and not be able to come up with two math functions that would just happen to meet that successfully, with one exception. And that's if this is a constant and this is a constant. If those two things are constant, these two terms grouped together are constant, these two terms are grouped together and are the same constant, and you just subtract those things off, well, then they will indeed add to zero. But the requirement is that these two things here, add up to be a constant, and these two things here add up to be another constant. Now, the constant we've chosen here is a wacky one. I'm not going to explain it other than to say Legendre came up with it because it worked really well for how he was going to index the polynomials that were the solution to these things, or functions that were the solutions to these things. And so all he meant here was like 0, 1, 1, 2, 2, 3. That product is the constant here. Like, so 0, 1 is 0. 1, 2 is 2. 2, 3 is 6. 3, 4, 12, right? That's what the constant is. And of course, this is the negative of that. And that pattern was important in indexing the solutions that are going to come about. All right, so if these two terms have to be equal to a constant, and these two terms have to be equal to the negative of that constant such that they're equal to 0, I just did that. I made these two guys equal to that, and these two guys equal to the negative of that. We refer to this is the radial equation. We'll come back and visit that come Wednesday. The equation, the angular equation, the one that has the theta and the phis, that's what we're going to deal with for the rest of the class today. Okay, and it might not be too surprising to you that when I try to solve the angular equation, which is both a function of theta and phi, well, I got two variables there. What's the technique? Go figure. I'm going to separate variables again, try to get that equation written in terms of only theta terms and only phi terms, and son of a gun, set them equal to constants again and solve those two equations separately. That's hence the name, separation of variable. So we'll work with this, this angular equation, and I just recopied it right here with the negative sign on my constants, 0, 1, 1, 2, 2, 3, etc. Okay, and the first thing I'm going to do, m here means multiply. If you didn't see my pattern before, I'm going to multiply by this y function, which is a function of theta and phi, times the sine squared of theta. So there it is right there. There it is right there. There's a typo here. Y sine squared of theta has to be right there. And if you see, I did get it right down there, but I dropped it right there for some reason. Sorry, I didn't proof it when I put this together. Okay, so that kind of helps out a little bit because right here, y is only a function of phi squared, I guess. And here's the separation I'm going to do. I'm going to say y, this thing I called spherical harmonics, and we'll refer to as spherical harmonics, which is a function of both theta and phi. We're going to break up into two functions, a theta function, which is only a function of theta, and a phi function, which is only a function of the variable phi. And I capitalized them to denote the function. The variables, of course, are the lowercase. And we're going to jam those guys right in there and right in there. Okay? And I guess, where else? Yeah, right in there too. So 3 places. Boom, boom, and boom. And so that's what I did here. Okay, there's the two things multiplied together. I dropped what the function depends on. I just put capital theta, capital phi, capital theta, capital phi, capital theta, capital phi. And let's see, once again, you notice that this term right here stayed. I don't know why I'm circling it. That term came out front because I'm taking the derivatives, both of them with respect to theta here. Phi is a constant relative to taking a derivative with respect to theta. And similarly right here, the phi stays, the theta can come outside the derivatives, which is what I did right here. Okay, and so that's handy. And then same technique I used before with separation of variables between r and y, the spherical harmonic and the radial function. I'm going to do the same thing here. I'm going to divide through by y. I'm sorry, in this case, yeah, y in this case, which is theta and phi in each case. So I divided through by the same thing 3 times. And some things cancel real nice like that and like that. And like both of them here, right? And so if you look now that I've done that cancellation, this first term only varies with theta. It's the theta function and the theta variables, okay, and the theta function. And this guy right here only varies with phi, the phi function and the phi variable. And of course, if you look at this extra term right here, you can see it only varies with theta. So it's going to be lumped with those guys right there. That term right there. And that's what I'm going to do on the next slide, I guess. Brought it over, and you see I brought this guy, made it positive, brought it to the other side of the equation, lumping it with the theta term. And this guy right here now, the first 2 terms are only a function of theta. The third term is only a function of m. Again, same math challenge, come up with 2 functions, theta and phi, such that the second derivative of one divided by the function is going to be equal to this function with a kind of a weird second derivative and add this constant on. Can you come up with two functions who, when you do those two operations and add them all up, will get you 0? And the answer is try from now till the day you die. You won't, with one exception, if both these guys and these guys are equal to a constant, and that constant is the same thing, and all I have to do is subtract one constant from the other, and sure enough, those would be equal to 0. Okay, and so that must mean this first thing in the bracket is m squared, the second thing is minus m squared. And much simpler constant than L times L plus 1 here, much more straightforward constant. And let's do the second equation right here first because it's much simpler. Okay, and so we'll call that the phi equation. That there it is right there, and we'll save the theta equation here for a little work on the next slide. Now let's solve this differential equation. First thing I did is I wrote it the way we more often do right here. Okay, and then I propose a solution here: a e to the I m phi, and let's see if that works. Because if I take phi prime, that would be I m e to the I m theta. And what I mean by prime there is I'm taking the derivative of phi with respect to little phi. And then if I go for phi double prime, that'll be, let's see, I'll bring down another im, so it'll be minus m squared e to the I wrote theta there, didn't I? What did I say? I meant phi right there, the variable's phi. And so I guess if I plug this guy right there, and I recognize that that is phi, so this is minus m squared phi, well, you can see minus m squared phi plus m squared phi, sure enough, is equal to 0. This is a solution, okay? Differential equations. However, I would think that Hamilton, or whoever taught you differential equations, if you did that for me, I would take off points for this, right? Because, well, this is a second order differential equation, right? How many constants do you have here? And the answer should be 2. And I don't see 2 constants there. And furthermore, if e to the I m phi is a solution, why not e to the minus I m phi as a solution? That's perfectly good solution as well. And so, I should have put a constant in front of that term and a constant in front of that term, like a and b, and added them together, and I didn't. So incomplete solution here, but it works, and we're going to go with it. And first of all, the way I take care of the fact that I've got a minus here and I don't have a minus here, it's an implicit positive, is let's just let m be a positive or a negative number, right? And then I've taken care of both solutions, okay? I think it's an integer too. Here's the proof that it's an integer. If you look at spherical coordinates, right? And there's x and there's y, and that's really all I need, but this is z. And let's see, there's my angle phi right there. Okay, and so if I have some function phi, which is math function now, which is a function of that angle phi, wouldn't that have to be equal to that function as well at phi plus 2 pi? Which means I'm at phi and I get that value. If I go all the way around one more circle, and so now I'm at phi plus 2 pi, those two guys have to be equal to each other, unless somehow phi is multi-valued, which we don't allow for wave functions, right? Wave functions have a value at a point in space. And so since phi and phi plus 2 pi are the same angle, they must have the same value of the wave function portion, the phi portion of the wave function. And so that would tell me that this guy has to be equal to this guy. See, I've just plugged in phi plus 2 pi. Well, this allows me to be broken up into 2 pieces, right? Because if I add the exponent, that means I'm multiplying these guys. And the only way this can be equal to that is if this thing is equal to 1, right? If that's equal to 1, then we're good to go. And we have made sure that the function phi isn't multi-valued. Well, what does that mean? Well, let's see. Remember, this would be cosine of 2m, I should have written it the other order, 2 pi m, but you got it here, I hope, plus I times sine of 2m pi. Maybe this is the right order, I don't know. We need that to be 1. what do you know about m if that's going to be true? Well, sine of 2 pi and sine of 4 pi and sine of 6 pi, those are all zeros. So I guess as long as m is an integer, we're good to go here. And similarly, cosine of 2 pi and 4 pi and 6 pi, those are 1. So m has to be an integer. M has to then be an integer, and it can be either positive or negative. And this becomes a better solution all of a sudden because of that. E to the I m phi is a great solution as long as I allow m to be either positive or negative. And if phi has to be single valued, that means that m must also be an integer in order to make this term right here be 1. The logic step behind that, and it kind of makes sense. Now, the constants, second order differential equation that we might have, well, we're gonna ignore them for now. We only need them when we solve the differential equation for the overall solution to the differential equation. So let's hold the constants in abeyance for now, and we'll tack the constant on to the theta function. Because, right, we just solved half of the differential equation right here. The theta piece, the theta piece is yet to be solved. We only did this. This doesn't have to have a constant because, remember, our overall solution is the product of these two things. So if the phi term doesn't have a constant, all we're going to do is we're going to make sure that the theta term does have a constant, the theta function does have a constant, and we should be good to go then. We don't need them in both places. We'd probably just combine them if we put them in both places anyway. So no value in that. So that's the deal, and that's what we're going to do. But we're, I guess, a third of the way solved on this Schrodinger wave equation in spherical coordinates. We've solved one of the functions, the phi function, and it's a pretty straightforward function, not too hard, and we'll use it again. So let's get back to this theta equation, and I'm not going to solve it. I'm going to tell you the answer. In fact, on one of the worksheets, I make you prove that one of the solutions is actually indeed a solution, and this is all the work of Legendre. And Legendre figured out that for this differential equation right here, which takes his name, the solution are these things called associated Legendre functions. And you can see that separation constant, L plus L times L plus 1. It shows up right there. And then the other thing that shows up is M. That's the same N as in the phi solution, right? When I said that phi is equal to e to the I m phi, that m right there is exactly the same n we're talking about there. And so Legendre gets credit for figuring out that since that m, let's see, where does it come in? It comes in right there because it's the separation constant. He realizes it's the same m that I had in the phi solution, so it must still be part of the answer. Okay, just to make sure we're clear, this term right here, I multiplied each term by that guy. And where did I put it? Ooh, there's a missing term right here. Right there. And so that became there. And I'm glad I checked this because apparently I'm missing a phi function right there too. So there's a second typo in this set, and it's right there. Of course, I didn't solve the differential equation, so it didn't matter. I'm just telling you that the solution to that guy, which is a differential equation, has this thing as its answer. And the proof will be plug it back in here, plug it back in here, plug it back in here, and see if it works. Okay, and Legendre, he had an odd way of writing this, and it's a little bit complicated. This must have taken him several years to figure out. Okay, if this is the solution right here, these things called associated Legendre functions, he further wrote that there's these things called Legendre polynomials, and you take derivatives of them to get associated Legendre functions. Okay, and the guy who actually figured out the Legendre polynomials, a guy named Rodriguez, is the guy who worked that out. I don't know if it's a grad student of Legendre or whatever. But in any event, these polynomials, right, just x squared minus 1, probably breaking up again, internet connection is unstable, raised to that L power. Now you can see the reason why that separation constant, L times L plus 1, might be used, because these things are key to these Legendre polynomials. And of course, Legendre polynomials, you take derivatives of them in order to get associated Legendre functions. And so we got to pull these things apart, and that's what the worksheet that'll be due Friday has you do. Let's work through some of these, and I'm going to start at the bottom because I got to get a Legendre polynomial in order to plug that in here in order to get a Legendre function in order to get right here, which is what solves Legender's differential equation. Okay, and just a couple things about these Legendre polynomials. If you've taken advanced E&M, I have no doubt that you've solved what's called Laplace's differential equation. And if you recall in spherical coordinates, for those of you that had the course, the solution to Laplace's differential equation in spherical coordinates are these Legendre polynomials. Now, it turns out they're Legendre polynomials not of x, but of cosine of theta, but that's the same thing we're going to have here too. So these are referred to as Legendre polynomials of degree L in x. And just let's follow this code a couple times. What is L0? Well, I guess I put 0 there. So that's anything to the 0 power, that's just 1. And now I'm taking a 0th derivative. Anybody know how to do that? Me neither. It's a constant, okay? No such thing as a 0th derivative. You can take a first derivative, a second derivative, a third derivative. There's no such thing as a 0th derivative defined to be 1. 2 to the 0 is just 1. 0 factorial is just 1. The answer for the Legendre polynomial of 0 is 1. Okay, keep going. L equals 1 now. That makes that a 1. I'm going to take a first derivative. 1 factorial is 1. 2 to the first power is 2. And so I wrote 1/2. The derivative with respect to x of this thing. Of course, the derivative of x squared is 2x. And derivative of a constant is 0. So I got 1/2 times 2x. The next Legendre polynomial is just x. So that's what we call P1. Okay, and one thing you might be noticing here, let me do one more and hopefully the pattern will be evident. If I do 2 now, that means 2 squared, 2 factorial, 2 squared, 2 factorial is just 2. I'm taking a second derivative of this thing, x squared minus 1 squared. Now, 1 over 2 squared for 8. There's the first derivative left, and then I've already taken the derivative of that, so that's, yeah, is that supposed to be, hang on. Yeah, I brought down the 2. Okay, I did it that way, as opposed to expanding it out. So I brought down the 2, make that to the first power, and then chain rule says 2x. 2 cancels that, makes it a 1/2. I still got to take the derivative on what's x squared times x cubed minus x. And so it became this thing when I did that derivative, 3x squared minus 1 with the 1/2 out front. And the observation here is, let's see, that's even. It's just a constant. This is an odd function. If you look back, this becomes an even function. P3, your expectation should be, I guess, an odd function again, and they alternate back and forth between odd and even. I think y must be a positive, I'm sorry, L must be a positive integer. Anybody know how to take a -1th derivative? Nope, don't got that. So L here has to be a positive integer because otherwise this definition doesn't work. I don't know how to take a -1 derivative, just don't know how. We already said that M must be an integer, okay, for exactly the same reason. We just reinforced it right now. And you may wonder, I called this thing down here a Legendre polynomial, but I referred to this thing as a Legendre function, associated Legendre function. If you look right here, if M is a even number, then these guys are polynomials as well. But if M is an odd number, it's really not a polynomial. This is a square root or a 3/2 power. And so that's why they're referred to as Legendre functions, associated Legendre functions, whereas these guys are referred to as polynomials. People refer to associated Legendre polynomials all the time. That's really it's a misstatement. I do it all the time as well. So do we all. But hopefully you can see why this is a function because it's a square root. These guys are always polynomials, right? X squareds, x to the cubes, x cubes, x to the fourths, all those sorts of things. And that's what's going on. All right. So we've kind of got a set of these polynomials I did up to there. If you look at what they look like, 1, that you can see why I said it's even. I'm sorry, 0, you can see why I said it's even. There's 1. Okay, there's 2, which is back to being a quadratic. That's even again. The cubic is odd. I've seen this. I found this on the web up to the 5th one in color code, so you can see what these polynomials look like. These Legendre polynomials, which solve Legendre's Laplace's equation actually in Cartesian coordinates. Okay. All right, so that's just what the functions look like. Now let's move on one because the solution that we need is the associated Legendre polynomial, which has as a piece of it these Legendre polynomials, associated Legendre functions, which have a piece of it, these Legendre polynomials. And you can see I have to take them and take a derivative of them, multiply it by this thing, okay, which is either going to be a polynomial or some kind of square root. And I get, well, let's do the first one. This is from the previous slide, right? I just brought those forward because I need them. And I'm probably going to only have time here to do a couple of them, but we're going to get a conclusion out of it, and then we'll finish up on Wednesday. If I go for the first associated Legendre polynomial, that would be L equals 0, okay? And that's M equal to 0. So I'm taking a 0th derivative, which is just 1, okay? So all that means is that's a 1 raised to the 0th power. That's a 1, 1, 1. Pretty good with that? Okay, so now the second one would be 1 with a subscript M0. Okay, so I'm going to put X right there, and then I multiply by 1, 1, 1, because M is 0 for all those. It just becomes X. All right, and now the next one, L is equal to 1, M is equal to 1. So L is equal to 1. That brings the X out, right? And so that's, let's see. Yeah, yep. Okay, I take the first derivative because M is equal to 1. That's why I wrote the derivative with respect to X of X, because P1 is X. And you can see I've got minus 1 to the first power. That's a minus 1. And then this term in the middle is 1 minus X squared to the 1/2. Well, the derivative of X with respect to X is just 1. And so the next associated Legendre function minus that thing, and then times 1. And so that's that guy. Okay. Here's the point, I guess, and we could probably quit after I do this. What if I tried to go 1, 2, where M is equal to 2 for L is equal to 1? So I've let M get bigger than L. Well, then I would be trying to take the second derivative of X. When I took the first derivative of X, I just got 1. When I take the second derivative of X, that's going to give me 0. The third derivative will get me 0. The fourth derivative will get me 0. Any derivative greater than this guy right here, okay? Well, one of the patterns you notice is if it's the first Legendre polynomial is X to the first power. The second one gets you to X to the third power. If you look at my table, the third one gets you X to the third power. If I start trying to take derivatives higher than that, I'm going to get 0 for all those. So M can never be greater than L. It can only be equal to L. So we've already said L must be a positive integer because you got to be able to take derivatives. We've now got a limit on M. And I don't have time here today, but if I do the same thing with the 2's, the L equal 2's case right here, okay, I would find that as soon as I tried to take P3, I'd be taking a third derivative on an X squared. It's going to be 0 as well. And that tells me that there are only 2L plus 1 possible values of M. So M can be equal to minus L. It can be equal to minus L plus 1, all the way to minus 1, 0, 1, and then all the way up to L minus 1 to L. If you count those up, say, for example, L equals 3, you'll have minus 1, minus 2, minus 3, minus 2, minus 1, 0, 1, 2, 3, 6, 7. 7 different ones, and the rule then is 3 plus 1, 2 times 3, that's 6, plus 1 more is 7. That's the number of possible values of M you can have for a given value of L. 3, 3, and the 0 is the plus 1. Okay, I think I'm going to call it quits right there. Other than to show you a picture of what they look like, these associated Legendre functions. And then what I've done here is I've substituted in place of X. I've substituted cosine of theta. This one you may remember was 1 minus X squared right there. So that would be 1 minus cosine squared, which is sine theta. And I plotted them. It's just a picture you can live with here and peruse. And I'll pick that up on Wednesday. We'll finish up associated Legendre functions. We'll look at them in 3 dimensions. Talk about spherical harmonics, talk about how we normalize them, and we'll look at the radial equation. I think I'm done. Sorry, I went over a little bit here today. We'll be around this afternoon at 3:30 for office hours. And unless you got any questions, let's call it a day. Questions? Anybody never seen anything I did today? You had Campbell's class, hopefully you did. All right, we'll see you later on. Have a good day.